All right. Well, good afternoon. This is Dean Carpenter, Program Scientist for the Albemarle Pamlico National Estuary Partnership, aka APNEP. Welcome to the second presentation of the new APNEP Science and Technology webinar series, sponsored by APNEP's Science and Technical Advisory Committee, aka STAC. So when STAC leadership proposed the webinar topic, primer on LiDAR, I had no hesitation on who to approach within our region. Today's speaker, Mr. Doug Newcomb. Granted, my response could have been his educational and career accomplishments, with a BS in geography from the University of Illinois and an MA in geography from the University of North Carolina, Chapel Hill. Then spending the past 34 years in different positions at the U.S. Department of Interior. Currently, Doug is a cartographer at the U.S. Fish and Wildlife Services, Raleigh Ecological Services Field Office, as well as co-chair of the Department of Interior's Open Source Geospatial Software Subcommittee, as well as the Fish and Wildlife Services representative on the 3DEP Emerging Technology Committee. In summary, Doug uses various open source geospatial software packages to perform his duties at work and to explore data at home. Admittedly, I was hazy on these details, but what drew me to Doug is that over the years, he would periodically share with me information on geospatial technologies and data, including new and or enhanced, often by Doug, LiDAR data, which was greatly appreciated. Note that this presentation is being recorded for later access via APNEP's YouTube video channel. Now I will hand the virtual mic to Doug so he may begin his presentation. Thank you.
Okay, let me get my sharing going. Now that I know how it works on here again.
Yeah.
And okay. You see my title slide?
Absolutely.
All right, then we're off.
Right.
Okay, what's LiDAR? Well, it's sort of an acronym for light detection and ranging. It's basically you shoot a laser, you hit a target, you measure the time it takes to get back to a detector, and the speed of light through air, time, this gives you the distance. You put that on an airplane with a very high resolution GPS and devices that will keep track of the pitch and yaw of the airplane to a very fine degree. Then you can hit targets on the ground and you end up with a point cloud of ground and vegetation returns and the occasional bird strike, if that bird's flying through there during the course of your data collection. So you've got different types of terrestrial LiDAR. You've got linear mode, which is the most common version of the aerial LiDAR. I'm sorry, the terrestrial should be aerial collected terrestrial LiDAR. Terrestrial LiDAR is a different beast in which you have rotating lasers set up on tripods on the ground. And I'm not really going to cover that today. The linear mode, you send out a pulse and you get peaks of the photons that return to your detector, and you call those the point returns, and you number them in sequence so you can have up to 5 or 6 returns from a single pulse in linear mode. Geiger mode, it counts the raw photons in the data and sort of it gives you the density. It processes down to the density of points that you require, and that uses a green laser. And you have to remember with that it's trying to describe things as a single photon, so all your return numbers are 1. There is a separate system out there called single photon data, which is still off and on in development, and it also returns XYZ coordinates for each photon. And once again, all the return numbers for that would be 1. Now, you also have topographic LiDAR, which I think you would, topographic LiDAR uses the near-infrared laser. That doesn't work too well. It doesn't really penetrate water, and when it hits water, it can do some really strange things and throw off your Z values. So when you're trying to do topographic work, you tend to use a green laser, which can penetrate between 1.5 to 3 Secchi depths. So when you do that, you emit it, and it bounces off the bottom surface if it can get through to the bottom. or it also gives a return at the top of this water surface, so you can get the elevation of the water as well as the bottom elevation if the water is clear enough for it to get to the bottom. That is a problem in a lot of our estuaries where you have very turbid water. Now, I've talked a little bit. We have quality levels for different LiDAR. The 2001 to 2006 LiDAR that was flown in North Carolina, the first time was probably about QL4 data, around there. The 2014 and 2015 data for the eastern half of the state was flown at QL2, which is 2 points, not per square, it's per linear meter. It's a point every, I hate it when people call me. And then it's just basically a 7/10 of a meter spacing between each nominal pulse. Whereas the QL1 data, which is what the western half of the state was flown in, and the 2020 data on was flown in, is 8 points linearly. Well, 8 points per square meter. It works out. Actually, it's more than that. But anyway, we'll get back to that. And you can go down to QL0, which just basically has a higher vertical accuracy. The QL2 data gives you a lot of data. The first three phases of QL2 data from 2014 to 2015 gave us about 360 billion points across the eastern half of the state, which is very useful to describe things. The newer data is not quite the same extent yet. You have the 2019-2020 topographic LiDAR, you can see on the right here. And then on the left, the 2020 QL1 terrestrial or topographic LiDAR. I say 16, I'll have to go back and recheck that. But that's very dense data, and it goes not quite to Raleigh yet. I think we'll go just to the west of Greensboro with the next phase that I think is being planned to fly next year, if I'm correct. But you can go to NOAA Coast Inventory, and it will tell you what data has been collected and when it, not when it will be, but whether it's available or pending. The other data that you might have available is there's a 2021 topography and then 2023 topographic LiDAR that is to the southeastern part of Virginia here, and also covers an area right here where there was a fire last year on Coast and Lakes National Wildlife Refuge. It burned the peat a little bit, so we're having we had a collection done in January to February of this year that to see if we can capture the difference in ground surface because of that. There's some older 2011 data that is available in this part of Virginia, right on the North Carolina border. And then you also have this 2018 QL2 data that's available. The point cloud formats, you can get it as ASCII XYZ. That was the only way one of the coastal data sets in the 2001 data was available. It was later converted to the LAS and LAZ format. PLY is a data format that you can use to, it's more for visualization. The ASPRS standard for LiDAR form data is the LAS standard, and I've got the link there. LAZ is the publicly documented industry standard compressed LAS format, and that's what USGS uses for default to download their data. If you go to USGS sites, everything is in the LAZ format. EPT is sort of an indexed version of LAZ, as well as COPIC is the cloud optimized version of LAZ. And the idea with those is that you'll be able to display the data remotely without having to download it, and just having, it's like tiles when you have a large raster, is that as you zoom in on an area, you get more and more detail. ZLAS is Esri's own proprietary compressed LAS format. I don't know of anyone besides Esri that supports it. And then you also have 3D tiles that are out there. It's related, but it's more for visualization than it is specifically used for analysis. The tools that are out there, GeoQ has LP360. That's been a long time standard for use. It's a commercial product. Esri's Arc Pro software has extensions that can handle LAZ data, but you can't use the standard LAZ format to process. You have to convert it to LAS or even to ZLAS before you can work with it. QGIS works fine, and I'll show you a few things about that when I get through here with the presentation. And then GrassGIS, I've been using that for over a decade to do LiDAR processing at landscape scales. Poodle is the point data abstraction library, and that's what QGIS and these days Grass uses as a backend library to work with the point cloud data. But you're going to do a lot of things from just command line utilities that come with that. And then there's also Global Mapper, which is a very nice program for working with point cloud data. But once again, it's a commercial piece of software. And what can you do with LiDAR? Well, the main reason that LiDAR is collected is for flood analysis, hydrologic modeling, so we can see where the flood zones are. And so bare earth elevations are one of the primary reasons people get LiDAR. And you can do sea level rise, and you can do some shorebird habitat with that. But the lasers tend to run into things like houses and vegetation on the way to the ground. So you can take that data and do vegetation analysis and habitat analysis for animals that depend on the vegetation. You can also do solar radiation modeling for rooftop and for habitats. And you can do viewshed analysis. So let's start with a little bit of shorebird habitat. This is one of our impoundments at Alligator River National Wildlife Refuge. And we fill these up during the waterfowl and shorebird migration seasons. And we could tell, fill it up to a specific elevation. We can tell how much of each depth class is in that. And then you can translate that for shorebirds into different shorebird and wading depth habitat classes, because different bird species have different leg lengths. They can work with different depths of water. And so when we have the impoundment filled up to a specific depth, we can estimate the habitat use for different bird species within that. And then you can go through and do an analysis at multiple elevations of the water level. And for each one of those elevations, you can calculate out what percentage of that impoundment are usable by the waterfowl or shorebirds. And just go on to vegetation analysis. And this is one of the first products I did from the 2014 data, was canopy height at roughly 20-foot resolution for the eastern half of North Carolina. And you can see the concentration there. The lower Roanoke is very high. You can see some of the areas on Alligator River down here at the Croatan National Forest, and see some of the interior Piedmont Forest as well. And then you can see the whole agricultural belt there in the intercoastal plain. Then skewness is a metric that I came up with to look at the distribution of points vertically from the top to bottom of the canopy. You can see in here there is a denser proportion of the vegetation near the ground than there is at the top. That's why you've got the nice blue color there. Whereas other areas you have more more of the, down in these areas where you have pine plantations, you have more of the density of the vegetation towards the top of the canopy. But also, you don't have to just look at just the canopy height. You can start looking at the concentration of points at different levels in the canopy. In this case, we're looking at 1 to 3 meters above the ground. And I just do a straight point count, 1 to 3 meters, divide it by the point count for the whole canopy, and you get the percentage of points that fall within that 1 to 3 meter. And once again, you can see the Pocosin swamp areas come up pretty well on that. And then you can also do 3 to 7 meters, but and there's still a fair amount of concentration here in the Alligator River Refuge area. You'll notice this area right in here where you have kind of a lighter, sparser thing for that. We found out after the fact that the instrument they used just in this area to collect, after it took the first return, it had a certain distance it would go before it would actually take another return. So it's kind of skipped getting some of the returns compared to the other instruments they were using. It didn't make me happy, but that's where it was. And the other way you can go is top down. You can look at the top of the canopy. You do a digital surface model, which looks for the first hit from anything, the ground, the top of a building, or the forest. And then you can look down from that and say, for example, here's an area on the Alligator River. And then this is the vegetation density in percentage points in the top 10 feet. And so you can see where you have a lot of shrubby, water, some shrub areas, but you have also a lot of areas where there's very few points in the top 10 feet. Then it may be an indication, for example, of if you combine that with canopy height, you may be able to pull out your ghost forest from that. So speaking of forest, you could all just say, well, let's set a divider between forest and non-forest between 5 foot. And then you can say, okay, where are the forest versus non-forest areas? And then let's start looking at what are the core areas. So I used our forest frag and grass, do 3x3, 5x5, 7x7 analyses. And what these do is that it sort of widens what the edge is before you get into the core. And then you can start looking at the different species of birds, for example. Which ones want a wider edge? What differentiation do they have between core and edge? And something like a robin, they nest in the bushes next to my front door. But some of the other deep forest species will really have preferences that you can pick out in this data. And then you can vectorize that and start looking at it. You can see some artifacts in there where you'll see where power lines are actually trying to show up that I can't really filter out easily, and that makes it think is that these are part of core areas. But if you start looking out and saying, okay, where are the contiguous core areas? If you look at the 5x5 fragmentation analysis, you can say, okay, these are the areas that have 1,000 acres or more of contiguous core forest. And then if you step back and say, well, if we need something that has a 7x7, has a wider edge, more sensitive interior forest species, then you can say these are the areas that by fragmentation analysis are the core areas for that species. So here's some exploratory work I did back in 2010, which is more a test of concept of the software, where I had a 60-foot canopy height from the 2001 to 2006 LiDAR data collection. And I used that to create a digital surface model and did daily solar irradiation modeling. So 365 days, I modeled the amount of solar irradiation that came to the entire area of North Carolina at a 60-foot resolution. And then I went back and took the canopy that was available, whether it covered streams or shaded streams, and tried to work out on a month-by-month basis how much those streams were shaded by both the coniferous and deciduous trees, and how many watt hours per square meter per year would impact those streams. And I did that for the whole state. And then I went back and did a comparison at like the first day of every month for a bare earth version versus the having the canopy filtering. And I found out that it's about without the filtering, the areas that I looked at had about a 64% more solar radiation hitting the water. That's just, it was just a test of concept. And the 60-foot data set was kind of something that I really want to come back and do it again with a 20-foot. There was a grad student at NC State University who went back and did at least the eastern half of the state at a 1 meter resolution. And I haven't looked at the results of his data yet, but I think it would be interesting. So sea level rise. You could also do sea level rise. One of the things I've been looking at is the sea level rise models to see how things would be impacted in the coast of North Carolina, because we've got a bunch of real estate there, wildlife refuges, and there are a lot of conservation lands and species there. So we know that shoreline losses occurred because I went back and did just for Alligator River, looked at some of the data from 1949 to 2022. And just for the footprint of the Alligator River Refuge, we've lost almost 23 square kilometers. A lot of that is erosion, but some of that is also due to inundation from sea level rise. And you can see the chime. If you do zoom into some of the areas that are low lying, you can see how things progress over time using the different orthophotography images that the state has been very foresightedly collecting over the time. So why do I want to do more of a straight model analysis? Well, NOAA's data things, they only show on their big maps inundation intervals at 1 meter or 1 feet. They don't do time-specific inundations. So if you wanted to look and do resiliency planning over the course of, say, the next century, you want to look at, well, if sea level rise is occurring, what extent is it occurring? What do the models say what's going to happen with sea level rise? And when is it going to happen? So how can we plan? And actually, it's not that hard to do. A workstation grade laptop with the right open source software can do it without breaking a sweat. I did a lot of this about 3 years ago during COVID, and they used both the 2017 and the 2022 sea level rise models. I'm going to show you some stuff based off of the 3 meter DEM, and I had redone the elevation data for the QL2 5-foot resolution DEM for North Carolina. Then there's a mean high or high water adjustment layer that you have to apply to convert the elevations that you have into mean high or high water, which is what all the sea level rise models use for their output. And I compared it to the USGS PAD-US and some of the natural heritage data. I also did some stuff with satellite imagery, but we're not going to go into that for this presentation. Here are the sea level rise grid source points. The points in blue are the 2017 grid points, where you have different models and their values at different time steps. The red 15s you see there are the points for the 2022 global sea level rise model, relative sea level rise model. And mean high or high water, that's the tidal datum that NOAA uses. It's the average of the high or high water of each tidal day observed over the epoch. For the purposes of these analysis, the epoch was from 1981 to 2001, and they generated the mean high or high water for that. You can do that at 6 months or a year. If you've got that data, you can look at what the mean high or high water is for that year and see how it, and use that as your adjustment. So for the 2022 models, the way it works is that they have 5 different steps: low, low intermediate, high intermediate, and high. And this is the elevation or change in sea level at the year 2100. And with each one of those, you also have a low, medium, and high component. So for the analysis I did, I generated over 150 layers. And as I said before, I created the relative sea level rise raster layers at 100 meter resolution. Created a single DEM of all the 3 meter data for North Carolina and Southeast Virginia, and that's a 15.2 billion pixel raster. That's not hard to do. And there's a whole presentation I can make on recreating the 5-foot DEM, and I'll touch a little bit on why I do it, and I need to update it. That was a 55 billion pixel raster, and that works fine in grass. And then I converted the outputs of both to mean high water by subtracting an adjustment layer that NOAA provides. And then I just said, hey, what areas are less than or equal to that relative sea level rise surface at every time step? And then you say which ones are ocean connected, and where are the areas where it's not connected to the ocean in DEM, but is still showing as inundated. You know, you have roads that form what appear to be natural levees in the DEMs. You don't have any kind of culverts or anything in there, so they probably are connected, but they're not in the DEM that way. But you still have to account for them. And then I just looked at how they compared to different features on the landscape that we can care about. This is just straight bathtub modeling, no sediment accumulation. The last two were left over for another presentation that is on YouTube with the North Carolina GIS conference. So this is kind of what the sea level rise models look like over time. And if you go through, you can see that you start seeing different shades to indicate different elevations. It's not just a straight one elevation across the coast of North Carolina. It varies across the coastline because it's relative sea level rise. And the coast of North Carolina is actually subsiding up here in the northeast area. And I think it may be holding its own a little bit down around Wilmington, although that may have changed in the past decade or so. So it's not a constant rate across the whole shoreline. And so you have to apply things differently. And as you go through all the way to 2100 here, you'll notice that my scale goes up to 130 centimeters. That's because even though it's a 1 meter sea level rise, North Carolina is one of those lucky places where the sea level rise is actually going to be higher than the global average of 1 meter. So back to the DEM. The original DEM, the NOAA DEM, was based off of the 2014 DEM. And I don't know why, but I do know that for Lake Mattamuskeet, the actual elevation of Lake Mattamuskeet in the DEM was about a foot lower than what the gauge height said in there. And so I have worked out a way to calculate an accurate sea level rise. An accurate water level for any impoundments based on the LiDAR data on the perimeter. And I've got a nice link to that presentation that I made at the Foster G North America last fall describing that. You basically run the iHydroflatten on a mean ground layer in grass. This add-on here that Dr. Anna Petrosova at NC State has written, and I've validated it with about 24 water bodies with USGS gauges nationwide to find out that the 12th percentile option for that run will give you the most accurate to date analysis of or estimation of what the water level actually is at the time LiDAR is flown. But irregardless of that, the year 2100 at a 1 meter sea level rise, this is what the coast is modeled to look like. The dark blue areas are going to be the areas that are inundated directly. The yellow areas are the areas that appear to be at the same water level, but are not necessarily connected to the inundation in the DEM. That's pretty substantial. And it affects just about all of our refuges. So I went through and did an analysis on to find what percent of each refuge was going to be impacted at different 10-year time series. So here are all our refuges for the coast. And then just doing a little preview. Here's Alligator River 2020 under the 1 meter medium model. And then if you go forward to the 2040, You can see where the darker blue is starting to come into the refuge a little bit more, and several areas and low-lying areas. So I just extend that on and do the analysis to look at the percentage of each refuge that's going to be impacted under each model. In this case, I'm just looking at the medium of the 5 scenarios at a 10-year interval. And you can see how the percentages are going to be impacted. For Alligator River, under the 2 meter, or even under the 2 meter, it'll pretty much be 100% by 2100. But you can see if you look down at the 0.3 of a meter, it's still going to be a little over half of the refuge at 2100. And this is the ocean connected, and then the disconnected, and then it's combined. The rest of these should be just combined. So Back Bay National Wildlife Refuge is going to be severely impacted. Cedar Island, of course, Currituck, the Edenton National Fish Hatchery will be somewhat impacted as well. Dismal Swamp will hardly be impacted at all. It seems to be above the sea level rise models. Mackay Island will be significantly impacted. And then if you look at Mattamuskeet, you can kind of see at the Mattamuskeet ones up here, the differences in if you do the correction if you do the correction to the elevation of the water level, it shows that there is a difference, but still going to be a major impact by the middle of the century. And then without the correction, you have just, it starts at a higher starting point. This Nansemond National Wildlife Refuge, that's up in Virginia. Pea Island National Wildlife Refuge has some high dunes. Remember, this is a bathtub model. So those sand dunes that are high up on Pea Island are still going to be sticking up under the model, but in reality, sand structure as the water comes up is going to start flattening out. And Poquoson Lakes is a little bit higher, so it will be later impacted, and then impacted to varying degrees depending on which model turns out to be the most correct. And as far as PAD US 3 conservation lands, I just looked for the total square kilometers of impact under each sea level rise model by 10-year increments. And you can see how many square kilometers are impacted. Even at the lowest one, you're going to have approximately 1,500 square kilometers impacted. And now we could also do the same thing by doing species. I took a species that really isn't going to be impacted that much, just to use as an example, Venus flytrap. It was a species of concern at the time. I was working on this. And then you just take the, it's not really a coastal species, but it does occur in some areas along the coast. So I just went through and ran the model against the polygons that I got from Natural Heritage Program for the habitat for that, and came out with the different between 0.2 of a square kilometer to just under 1.2 square kilometers. And you can see this, how this works. We'll zoom in here on a part of Stumpy Point, where you can see that this is the 2010 imagery and what the 2017 model showed. This is from the 5-foot redone DEM that I did. And you can see how the water the modeled water is actually showing up fairly close to what is there. And in the 2020 imagery and the 2017 model with the 5-foot, the quick DEM really showing how it's showing up, the extent the water is already at follows pretty closely with this model run. If you look at the NOAA 3-meter DEM, you don't see as much of that. And I think part of that is the way the DEM's constructed. These areas of open water are below the 2 acre minimum mapping unit for 3D break lines. So the way that they create the surface through here is by using tins. They create triangulated surfaces between ground points. And that over open water areas tends to form ridges that are higher than the actual water surface. So the ground surface, in my opinion, is actually misrepresented, or the water surface is misrepresented in these smaller areas, which is why I was inspired to come up with that other method that I referenced earlier. So what's the next steps? Well, I'd like to rerun the model intersections against a 1 meter DEM from the 2020 QL1 LiDAR data. And I might go back to the 2017 model as well as the 2022 model to get changes between 2000 and 2030 and look at that on that model run as well as the 2020. It's just the idea of which model is best matching up with the current water inundation. I probably won't go as far west as I did with the first one. And then I'll do the impoundment elevations using the R hydro flatten with 10th percentile per the per what I found in the research. And I would thinking about doing a temporal interpolation of the sea level rise models at 1 year intervals between 2020 and 2030 and try to match that up with whatever satellite or aerial imagery might be available to see which one matches up with the best with the which model matches up best with what's going on with North Carolina. Okay, and that's all of the presentation. Before I jump into the demo, are there any questions? And let me see now. I'm still I hear a microphone. Okay. I hear somebody's sound is squeaking like a mouse. I can't really hear a question though. Is that you, Don? Just type it in chat. I see your hands waving, but just type it in the chat and then I'll try to answer it there. In any event, I've got some sample LiDAR data from right around, no, that's not what I'm looking for. That one, that's it right there. And, you know, a QGIS allows you to do 3D visualization of the point cloud itself. This is the Wright Brothers National Memorial. So you can see how these are the not ground points. These are the unclassified points. And this is from the Topobathy Green Laser LiDAR collection. That was done 2019 to 2020. And you'll notice over here are the different classifications. There are some high points that are probably bird strikes. If you look, you can see these individual points up here, which show you the dangers of trying to do canopy heights just by looking at the maximum value. You have to have some sort of upper boundary. There's an R routine for LiDAR that I think takes the 95th percentile, and that will exclude points like that, give you a better canopy height as well. I usually just use grass and cut off the values at 250 feet above the ground surface, because the tallest tree we have in North Carolina is about 200 feet when I'm doing canopy heights. But this is, it looks nice, and if you look in here, you can almost see the boles of the trees. So you can get some really detailed data. And then you see the power lines over here. I've got if I thinned out the representation of the dots a little bit, it would be a little bit finer. And then you can see the houses over here. You can see some gaps in here where that you're looking through the data. I don't have the ground points in there, and there are no ground points under these houses. So that kind of gives you a little bit of eye candy of how you can display the LiDAR data directly from the LAZ files in QGIS. Let me pop in another QGIS thing here. Not that one. Let's see, I want that one. Okay. So this is another LiDAR data set. And instead of from a local LAZ file, this is grabbing the data, the point cloud, from a web service out on Amazon services, Amazon's cloud. And I'm just displaying the data that way. And there are ways you can pull the data down and process it as well. And it just will populate the data more densely as I go in. So it's a way of being able to visualize the data without actually downloading it to your computer. And I think the COPEC format, COPC, Cloud Optimized Point Cloud format, will allow this to happen as well. And I think USGS is looking at that as a potential way of distributing LiDAR point cloud data to be visualized fairly easily. It's an open industry standard. It's not an OGC standard as of yet, but for right now, it's what everybody is using, both the LAZ, the EPT, and the COPC coming down the road for that. We switch back to this, and I'll turn off the 3D map for a second. And what you can do is I've just got two of these right here. And one of the things that the QGIS client allows you to do is create virtual point clouds. So I'll turn off the layer styling here, open the processing toolbox, and you have these specific tools in the toolbox which allow you to work with point cloud data. And in this case, I'm going to create a virtual point cloud, and I'm going to go to the inputs. I've got, see, I only want two. I've got one in there twice, I think. So I'll just select these two right here. And I'm just going to, in this case, I'll just save it to a temporary file. And what this is doing is it's creating a virtual point cloud, which allows me to process with the other tools as if these were a single entity. So for example, if I want to export to raster, so I'll take the virtual point cloud, and I want to have a 1 meter resolution raster output from it. And then I can say, okay, I just want to use the ground points. And well, we include that. I'm going to filter out just the things I want. I don't want intensity. I want the ground points. I want in this case, it's 13 and I believe 14. No, wait, we're working with the NOAA data. So two will do it. So 2 and 10 and that should do it. All right. And I'll test that. Yeah, it's successfully parsed. Say OK. And then I'll just say run. And I'll create that as a virtual. Oops, what did I do? I, of course, did something wrong. Don't you know what? I'll have to go back and do this again. Let's try saving that to a file. I'll just call it test. Let me see if that will do. I obviously have something wrong in there. Attribute Z. Attribute Z. Well, let's go back and clear that out and put classification equals 2, and we'll just 2. ground. We'll just give that a shot. Oh, well, I'm doing something wrong. I do this every time. But when you do it right, you can actually get a 1 meter dim out of this. And from the ground points. And you can see the gaps in the buildings there. The ground points are missing. They don't have ground points under the buildings. When you use the hydro flattening algorithm, it also flattens underneath the buildings, so you get a flat surface under every building, which is going to approximate what the ground surface is at the building foundation, which might be useful to folks as well. But that's pretty much all the demo I have, unless anyone else would like to see anything else. Do we have any questions, comments? Are my speakers working?
Doug,
I
this
not
is
see any
Hans.
virtual hands right now.
Oh, okay.
Can you hear me?
Okay, Hans has his virtual hands up.
Okay.
Yeah, I got my Hans up.
Yeah.
Okay, Doug, beach renourishment,
Yeah.
huge issue here.
Right.
In terms of why are we spending so much money on it when it can disappear, with one event? Is that something that can be, documented and used to actually evaluate, whether it's worth even doing it in some areas?
Yeah. Okay. That's a good question. The thing is that LiDAR tends to cost a lot.
Well,
and
probably
and-
relative to beach renourishment, it may not be that expensive. I don't know.
Well, there are several options. It depends. If you were to do, I think it might be worthwhile to, instead of, you can do LiDAR for a situation with the beach. Let me stop sharing and I'll start, stop sharing thing and I'll get myself oriented so I'm actually talking to you instead of at you sideways. For a beach, I think you might actually be okay if you would just do sections with a drone and do structure for motion. You can use Open Drone Map with several of the drones that are out there, and as long as your control is good, you have a good enough GPS unit in your unit associated with the photos, then I mean you could get 2 centimeter resolution imagery and get a very dense point cloud directly from your images. And Open Drone Map would be a way to start because, for one thing, it's free and it does a very good job.
But you'd have to fly your drones.
Right, you'd have to fly your drones, and that's the other thing, because for the LiDAR data, we have data from 2001, 2014, 2020, or 2019, 2021. So, and shorelines can change on a daily basis. So I would say if you're going to do that kind of analysis for shorelines, then I think it might be more economical to pick out areas that that would be sample areas, like 30 areas along the shoreline, areas that have control areas as well as areas where sand is being introduced, and then do a regular, I would almost say weekly. I wouldn't probably go to monthly, but I'd probably do something like a weekly drone flight over those areas and see what you can do. And depending on the drone, you can get some fairly substantial areas. I was just talking to someone from USGS who had used one of the newer Wingtra drones, which is vertical takeoff, but it has wings, and it has a very good endurance. And I think in 4 hours with a LiDAR attachment on that one, he said they were able to collect about 1,000 acres. So that puts something like a weekly or even something like that into it could be something that could be workable, I think, for if you have a sufficient effort. Don, you got your hand up.
Yeah, I'm going to try one more time.
Oh, I hear you. Great.
Sorry, I wasn't being a lot lazy. I have the squeaky mouse syndrome, and it's just easier to bug out of the whole program and then come back in. Couple of things, comments. First of all, thanks for that QGIS demo, because I hadn't had a chance to look. That's some pretty impressive tools for something that's that I have access to for free.
Yeah.
That's pretty impressive.
And I probably screwed up the data. That's why it wasn't, because I've done up to 400 tiles in a single shot with that virtual. Not only being able to create a virtual that large, but being able to process the mean ground over that many tiles in one shot. I think there was a limit last year on how many tiles you could do. I think 300 or so was about that limit, but they did some work over the past few months, I think, on the Poodle library. I think for the issue it was basically, it was the number of characters in the command line they were passing to it. You would run out of character string in the back end of Windows and Linux. It was just different lengths for that thing, and they worked around that. But sorry, yeah. I cut you off completely, and keep going.
Yeah. Well, no, that's cool. The other thing is, to Han's point, in what you were talking about, I'm just impressed. You know, I know they have it at the Duke University group.
Oh yeah,
drone group. They've got LiDAR. You know, I know UNCW's group is, everybody's. You know, they're out there. So you could, and what LiDAR I've seen from drones, I've been impressed with. But before I forget, a question, just because I should know this, and me and you have probably discussed it, but in one of your earlier slides, of course, you showed to the right, well, to my right side, you showed the 2019-2020 topo bathy.
Right.
And then I should know this, but then off to the west of that, there was a large, red, green, colorblind, green area that I think was 2020 LiDAR that you were talking about.
Yeah, that's the topographic LiDAR that was also flown. They did a joint project where NOAA flew the topo bathy, the entire North Carolina coastline going up into the estuary in Virginia. Right. And I think they cut off, they didn't quite go up into the Albemarle Sound all the way up to the Virginia border with that. But you also had the QL1 data flown. This was post Florence for that other area going inland. So you have topographic near infrared LiDAR flown there at full QL1. You've got a posting distance of kind of, the 8 points kind of confuses me what they've got up there, because, you know, it basically, your posting distance is 35 centimeters. So you're going to have 4 points within each meter linearly. So if you extend that both ways, you should end up with about 16 points, depending on what the spacing is between but it's pretty good stuff.
Yeah,
and
no,
it's much better. I've already compared it to the 2014 data. When they flew the 2014 data in that Albemarle Peninsula area, there was a lot of water on the ground, and the interpolation between the two data sets, because of the amount of water, I mean, I've found some areas that up to 0.4 of a meter difference, just because it was flattened out because of inundation. And so I'm really, really happy with what I've seen of the 2020 topographic LiDAR so far. And I hope to really, if I can get enough time, go ahead and redo it. The state has already started putting out some, they have reprojected all the data from NOAA and USGS from UTM zones into State Plain feed, NAT 83, 2011. And they've started putting out products on a county basis that you can download right now, but they're all tin-based, even across the water bodies. Like if you look at Lake Mattamuskeet, the water level varies as you go across it because it's big triangles. And I'm hoping that's probably just an initial product they wanted to get out because we got a hurricane coming up and you want to get those land surfaces done, something out there for the upcoming hurricane season. That's my personal guess, and because you want to have something out there that's recent. But I'm expecting they'll probably come back with a product down the line that will have those water bodies with flatter elevations in them.
Cool. Thanks, man.
I mean, I'm fully confident they will. They're good people. Yeah, you can go and download the county data sets that they have right now at a you can get I think it's a 3.125 foot resolution, about a meter. And I downloaded Hyde County for Lake Mattamuskeet, and it's an uncompressed GeoTIFF. It's about 7 gigabytes for that. You can do a little bit of Google command line and compress it and put overviews in, and it works just fine. Any GIS I've got.
Cool.
Yeah. So it's all. I'm looking very much forward to working with that new data if I can get the time to do it.
There you go. Frank, I see one more hand up there.
Okay,
Yeah.
who else we got? Frank
Hey,
Mark?
can you hear me?
Yeah.
Awesome. Thanks for the presentation. I guess I had a quick question and then a comment. You mentioned that there's going to be data collected in 2025. Is that going to cover the whole coast? And then is it going to be?
I don't know that I mentioned 2025.
Oh, okay. I thought you said that there was a plan to, you were starting to plan to collect data sometime in the near future.
I know that NOAA and Corps of Engineers, they do regular coastal collections for navigation and shoreline. That kind of got upset because they also fly when you have a hurricane come by nearby. So we have had data collected in 2019, 2020. That was the main topography effort. But we also have, for a good portion of the coast, we have a 2021 collection.
Yep.
I think there was also a Corps of Engineers effort that took in the whole coast earlier in 2020. So you've got a fair amount of right on the coast data. The efforts that Corps of Engineers do is that they will fly topography 1,000 meters out and 500 meters in. One of the exceptions is Pea Island, where I asked them to fly a little bit further in so they completely cover our impoundments. So they do cover that. So you will have, on the extreme coastal data, you'll have that. I think the 2025 date for the LiDAR collection, I think that is for the central Piedmont. That's not for the coast. I think it's been proposed. And I think that would be outside of the APES area. So,
Okay, yeah, that was my question.
Makes me excited, but unless we have a major hurricane this season, in which if we do, then we'll probably have another round of LiDAR flown at least on the coastal areas, topography, because that things will change.
Okay.
It's a. Do we have any other questions? And I've used up the whole hour. Oh, Hans has got one. All right.
I got one more. This is going to be the most stupid question of the day.
No, not at all.
Can you use satellites for this?
There is a
And the reason I ask is because, getting back to my beach renourishment thing, you know, if you had a satellite that flew over, you know, at least once a week or something, you know, you wouldn't,
well,
you
you
know,
get into the horizontal accuracy issue, and there's a topographic laser on the space station, Getty, but the horizontal accuracy of that is about 10 meters.
oh, okay.
Yeah, and there's ISAT-2, and I don't recall off the top of my head what the horizontal accuracy of that one is. The fun thing is that for ISAT-2, I think the satellite itself travels about 20 meters between the time it shoots the laser down and the time it gets back up to it. So it's I hesitate to say, because I don't remember off the top of my head what the horizontal accuracy is. It's great for and it doesn't do the whole ground. Both of those just do strips along the ground. They're not continuous across the whole ground surface. One thing that you might investigate from the satellite standpoint are some of the synthetic aperture radar satellites that I know that some of the commercial ones, for example, it's not a preference, it's just one of the first one that comes up is Umbra. They have a sub-meter X-band radar that I think you might be able to pull out the shoreline from that. But you have to, and NASA, I think, may have a research option for acquiring that data if you're just doing it in constrained geographies. So that's a possibility. You would just have to go through one of your governmental sponsors to go through the CIDR process to set up to get a regular collection over a location. But it's not going to be the whole coastline. For something that high resolution, I don't think it would even cover all the impoundments in Alligator River Refuge in one shot. It's a fairly tightly focused when you do things at that resolution. You can go high resolution. Or you could work with something like Planet and get your daily imagery that way. And with the 4-band data, you can do a water difference index that I don't know how that would work with surf, though. That's the only issue. So all that being said, and it all being tidally influenced, the reason I suggested the drone option is that it's something that would be fairly inexpensive to do with orthophotography from a drone. The expense would be going out there. You would probably have a set of grad students that would be doing this section today, that section tomorrow, that section tomorrow, and basically traveling up and down the beach the entire year. And that would be their day. So, or if you could hire somebody else to do it. So, you know, the satellite SAR data or Planet that does daily 3-meter imagery, those might be options if you were looking at trying to track what the shoreline's doing. And Planet's data goes back several years. I mean, I think they started doing the 3-meter stuff back in 2020. So
Right.
so that is something you might be able to have. NASA has a research agreement so that if you are coordinated with one of the federal agencies, you can get that imagery as part of a research objective at no cost. But it has to be research. It can't be something that is for, say, if a refuge manager wanted to keep track of the vegetation on his refuge for day-to-day management. That doesn't qualify. But you could reach out to the NASA folks and ask about their commercial satellite program. And,
Thanks.
yeah. So That gets way off topic.
right. Well, I really appreciate your contribution, Doug. I really appreciate it. And again, it'll be made available to others soon enough on the APNEP channel, so YouTube
Yeah.
channel. So
Yeah.
again, thank you very much. And everybody else, have a great day.
All right.
Take care.
Bye.
Thanks, Doug. Have a good one, folks.